definitions are being used to describe the system. So this is another mathematical requirement, or you can say the compulsion we impose on the function psi, that it should be linear. And third, which is the most important quantity which we are looking for, is that it should be homogeneous. I will not go into the rather mathematical detail of what do we mean by homogeneous wave equation and inhomogeneous, but we can say that homogeneous wave equation means, as shown in the slide, that when we find the probability by mod psi square over the entire space, and when we integrate, then it should give the 1. The physical justification is quite obvious. As already suggested, statistically, mod psi square represents the probability of finding particle, and if that probability is integrated from the in an entire space, and if the particle is somewhere in the space, then obviously the total sum of probability of finding particle will be definitely 1, because particle is there and you are sure that particle can be found in the space. So the integration over the entire space will be the 1. In another language, the same thing when we say, then we say that your wave function psi is normalized. What is normalized wave function? What is the requirement of normalized? That we'll just discuss. But right now we say that normalized wave functions has the total probability over the space 1. That means somehow by performing some mathematical trick also, we'll be able to write a wave function in such a way that that wave function gives the probability of finding particle in the space to be 1. So these are the mathematical requirements, that your Schrodinger equation should be a first order differential equation because of the initial condition can be used. It should be the linear wave function psi should be linear in order to observe the interference or the superposition, and it should be homogeneous. That means the probability of finding particle in space, somewhere in the space, must be 1. With this mathematical requirement, now let us also discuss that what are the physical demands. See, in physics, in fact, we are dealing at 2 fronts. One, we are also interested to solve the problem mathematically by having some knowledge of the mathematical tricks and mathematics, and at the same time we will be able to interpret those mathematical equations in terms of physics or in terms of the physical requirement. So let us also go into the physical aspects of that, what this wave function supposed to be, and whatever mathematical conditions we have just discussed, that how they are being useful in describing the actual or the physical conditions. Let us concentrate again on what, as I've said, that our wave function psi should be linear. What it means physically. If we solve the Schrodinger equation with this property, that a wave function psi is a linear function, then definitely we come across the constants of integration which are appearing in the equation. They will not depend on the state of system. That means the earlier problem that for different systems the form of the Schrodinger equation is different can be circumvented, and we can get rid of this requirement that the wave function should have the parameters which are independent of the state of it. And second property, that homogeneity, as I've discussed, is required in order to find the total probability of finding particle to be 1, and that also leads to the conservation of probability. If at some place the probability of finding particle decreases, that means there is another place where the by same amount probability of finding particle will increase. So we have this interpretation on the wave function, that what it will suggest. As I've said, that the probability for a particle in the entire space supposed to be 1, and that leads to the concept of normalization. The constant appearing in the wave function should be adjusted in a such a way that the total probability of finding particle gives the 1, the surety. But there are certain conditions, there are certain situations where the probability may not gives the 1. For example, I have quoted the 2 examples. Whenever we come across the scattering experiments, or whenever come across the chain reaction where the neutrons are ejected out, then these neutrons are in fact cannot be treated by the wave functions which gives the probability 1. Such a wave functions for which the normalization is not 1, the probability is not 1, are known as the non-normalized wave function. Their interpretation for a non-normalized wave function is quite different for that the normalized wave function. In a normalized wave functions, as we have already discussed, that it gives the probability of finding a particle, but the same interpretation is not holding for the non-normalized wave function. And then we have to talk about the either relative probability, or we may also interpret the normalized wave function as the large number of non-interacting particles confined to a single region of space. In that way, it is equivalent to a statistical ensemble of isolated system. As I have said that they are non-interacting, so they are isolated from one another and they move their own without interfering the presence of other. So such a interpretation is also true for the non-normalized wave function. Finally, after knowing this, that the statistically we have what are the interpretation of wave function, let us spare 2 or 3 minutes to discuss about what are the admissibility conditions on a wave function. What are the mathematical conditions that has to be taken care while describing the wave function? Number 1, it should be finite everywhere. It cannot give the infinite value, otherwise the probability of finding a particle gives the infinite value, which is physically not possible. It should be a single valued everywhere. Obviously, the particle, if you find at some place, at some time, and later on, it should give the same value. The probability of finding particle at the same position at a different time should not be different. This 2 requirement in fact comes from our probabilistic interpretation. Other 2 conditions are in fact comes from the depending on the potential also. So it should be continuous and its derivative should be discontinuous. So in the last slide, I conclude with this, that the wave function basically describes the state of a quantum mechanical system, and it is mathematically it forms the complex linear vector space. Thank you very much. Thank you all.
SANDHAN, All Gujarat Integrated Classroom.
સેટેલાઇટના માધ્યમથી જોડતી કડી એટલે સંધાન.